Hello, everybody, and welcome to today's presentation. Make your Java applications run even faster. Brought to you by Azul Systems. I would like to introduce you to our presenter, Simon Ritter. Simon is the Deputy CTO of Azul Systems. Simon has been in the IT business since 1984 and holds a Bachelor of Science degree in physics from Brunel University in the UK. Simon joined Sun Microsystems in 1996 and started working with Java technology from JDK 1.0. He has spent time working in both Java development and consultancy. Having moved to Oracle as part of the Sun acquisition, he managed the Java evangelism team for the core Java platform, Java for client applications, and embedded Java. Now at Azul, he continues to help people understand Java as well as Azul's JVM technologies and products. Simon has twice been awarded Java Rockstar status at Java 1 and is a Java champion. He currently represents Azul on the JCP Executive Committee and on the Java SE Expert Group, JSR 379, 383, and 384.
Okay, well, thank you very much and welcome to this webinar. The idea behind this webinar is really to explain to you about what it is we do at Azul in terms of being able to improve the performance and reduce the latency associated with Java applications without you having to change any of your code. So this is purely in terms of how we change the Java runtime, the Java virtual machine. So I'll explain through all the different things that we do from quite a technical level so you can see exactly what it is that we're able to do to help you run your applications faster. So the first thing that we need to talk about is understanding how the JVM works in terms of its effect on the performance of your application. And so what I've put together here is a very simple graph, which is what you would like in an ideal world. So if we look at this graph, what we're saying is that if you had a perfect JVM, then this is the performance you would expect to get from that JVM in terms of running your application. And by this, as you can see, it's very simple, very straightforward. So when we start our application, the JVM runs at 100% of its possible performance, and it does that straight away, and it continues to run at 100% of its possible performance all the way through the time that you're running your application. So that's exactly what we want. However, what we actually get is something that looks a bit different to that. So if I change the graph, this is a much more representative graph of how the JVM works and delivers performance to your application as it runs. And we can see that as the application starts off, it starts off quite slowly. Now, the reason for that is because Java uses bytecodes. So rather than compiling your application into native instructions for an Intel processor running Windows or for an ARM processor running Linux, it uses bytecodes, the virtual machine instruction set. When the JVM runs your application, initially what it does is it has to read those bytecodes for the classes and the methods and so on that you're going to run, and it has to convert those virtual machine instructions into the instructions that are appropriate for whichever machine it's running on. And this is where we get the marketing phrase that Sun originally created, which is write once, run anywhere. So you don't have to recompile your code because it's using bytecodes. But the problem is that when you do that, JVM has to interpret those bytecodes and it has to convert it to the right instructions for the particular machine. And it has to do that every time it sees a particular bytecode. So there's no concept of caching the information or anything like that. So every time it sees a bytecode, regardless of how many times it's seen it before, it has to do the same thing. And this is why Java used to be criticized as being slow when it was very early in its development. In order to change that and to give us better performance, what happens is that the JVM will start looking at the bytecodes that it's running, and it will start to profile, it will start to track which ones are being run more frequently. And it does that in terms of the methods that are being executed. What will then happen is that the JVM will notice through the profiling that it's doing and gathering statistics that certain methods methods and certain instructions are being run through, let's say, a loop. And a loop runs thousands of times, and the JVM will see that that particular set of instructions, those methods, are being run every time through the loop. In order to improve the performance, it will take the code of that particular loop or a particular method, and it will run it through a thing called a JIT compiler, a just-in-time compiler. And the way that works is it uses a thing called the C1 JIT compiler. The C1 JIT compiler is designed to compile code very, very quickly. So we want to get the code compiled so that we can run it straight away. But what it doesn't do is optimize that code in any meaningful way. It will compile the code into native instructions, but it doesn't optimize it in a way that would really make it run very fast. But we get the code quickly because it compiles it fast. So that's where we see an improvement in performance, but only a gradual improvement. The JVM will then profile that application and the code that's been compiled, and it will do more in-depth profiling to see which particular branches of if statements are taken, which particular pieces of code are run within a method, which pieces of code are not run, and so on. What it can then do is it can do a second compilation, and in this case it uses the C2 compiler to recompile that code, but applying a lot more optimizations. So it takes longer to compile the code, but it's able to look at all sorts of different ways of improving the performance of that code. And so that's what we see in terms of the improvement in performance. But you'll also notice there are some significant dips in the graph as it gradually moves upwards. And what those are what are called de-optimizations. De-optimizations occur because the compiler will have to make, or will make, certain assumptions about what the code is doing. And these are called speculative optimizations. Speculative optimizations are basically where the JVM will notice that your code only ever goes through one particular branch of an if statement. And so it will optimize the code based on it continuing to only go through that one branch of the if statement. What might happen is at some point in the future, you get a different situation and your code then needs to go through the other branch of the if statement. So it used to be it was always true, suddenly a false comes through and you have to go through a different branch. In order to make that work, the compiler has to throw away the code that it's compiled because it was designed to work only if it went through the true branch of the if statement, and then it has to recompile it so that it can deal with both sides of it. And that way we get what's called a de-optimization, so we have to go back and recompile the code. So after a while, we get to a steady state where pretty much all the code that's run frequently will have been compiled. It will have been compiled with the C2 compiler to give as much optimization as possible. We'll have passed all of the various speculative optimization, de-optimizations. But we still see various dips in the performance of the application. And the reason for that, once we've done all the compilation, is garbage collection. So garbage collection is the other part of what the JVM does mostly, and at certain points we need to reclaim the space that's being used by objects that are no longer referenceable, and then make that available so that we can create new objects. So we see these dips in performance. So this is the reality of the graph, and what we need to do is to change that to make it more like our perfect graph. So the big challenges that the JVM has is that it is what's called a managed runtime environment. So it does a lot of the work that the developer would typically do if you were writing C or C++ code. So it handles things like the fact that you don't have to allocate memory explicitly and then free that memory explicitly, things like that. And so this is the thing. We have this garbage collector. And the problem, if you like, with the garbage collector from a performance point of view, it's very good in terms of helping you not get memory leaks and dealing with the issues of garbage collection. But it is inherently non-deterministic. You can't predict when the garbage collector is going to run. So you can't say, well, every 5 seconds I'm going to see a little dip in performance because that's when the garbage collector runs. No, it runs when it needs to, and that isn't easy, if at all possible, to predict. The other thing is that for pretty much every algorithm that garbage collection uses, you can get some very long pauses because it has to go through, and depending on what you're doing, it may have to compact the memory, it may have to move objects around and do that in a way that has to pause your application threads whilst it's doing that to do it safely. So these are two things that we need to kind of be aware of. The second thing is, as I've already said, the fact that we use bytecodes and not machine codes. And so how the JVM approaches compiling the bytecodes into native instructions has a significant impact on how well the application will perform. And this whole idea of a warm-up phase in your application, it will take a certain amount of time, could be seconds, could be minutes, before it gets to the optimum level of performance that it's able to with those compilers. So the question we have to ask ourselves is, what if there was a better JVM? What was it if there's a better way of doing this? And the answer is, there is. And we call it Zing. So Zing is our JVM, which is designed to reduce latency and improve performance. Let's talk about how we actually do that. So in terms of what Zing is, it is a JVM. And we start off with the OpenJDK source code. So this is an open source reference implementation for the Java SE standard. We take that and we modify it in terms of the garbage collector, in terms of some of the compilation. And then once we've done that, we make sure that it still is fully conformant with the Java SE specification. So we run all of the TCK tests that are part of the JSR. We run all the JCK tests, which are the Java compatibility tests, to make sure that if you run Java on Zing, it runs in exactly the same way as it would on Hotspot or J9 from IBM or anybody else's JVM. So this is exactly the same. It's the drop-in replacement for any other JVM that you're using, say Hotspot. The only thing that's going to change is some of the command line flags will be different. And mostly, you just have to remove most of the command line flags that you use because they don't have an effect on the Zing JVM. But we'll talk a little bit more about that later on. It only has one garbage collector. So there are several different garbage collectors that you can use if you're running Hotspot. There's things like CMS, there's things like G1, there's the parallel collector. With the Zing JVM, there is only one garbage collector, and it's called C4, the Continuous Concurrently Compacting Collector. Now, this works in conjunction with some other things that we have, which is called the Zing System Tools. I'll explain that a little bit more on the next slide. The other thing that we've done is, as I say, we've modified the compiler. So rather than using the older Hotspot C2 JIT compiler, we have a completely different compiler, which we've called Falcon. Reason for that is that Falcon is the fastest animal on the planet, so we decided that we're going to have the fastest JIT compiler. We'll call it Falcon. And the other thing that we've done is to look at how to reduce or as far as possible eliminate the warm-up phase. We have a thing called ReadyNow. And ReadyNow, as I'll explain later on, essentially takes a profile of a running application and then uses that when you start the application again to avoid a lot of this warm-up phase that you need to go through with optimizations and de-optimizations and recompiling code and so on. But again, we'll explore more as we go through. Zing System Tools. So the idea behind Zing System Tools is that if you look at the way that an operating system works, you have memory management built into that. So an application that runs on top of Linux or Windows will require memory. You have physical memory in the machine, and there needs to be a mapping from the physical memory into the addresses that are used by the application. Now that works very well, but it's designed for general purpose applications. It's designed for all sorts of different applications. And the JVM is a very specific application. It uses memory in specific ways because of the design of the heap space, because of the design of the way the garbage collector works, and so on. So what we've done is we've said, well, rather than having the operating system use a general purpose memory management system for the JVM, we'll actually change that and we'll create a new one which works in conjunction with the operating system to improve the performance of the memory management system at that level so the JVM can work even faster. So what that allows us to do is some nice things to improve performance. So one of the things we can do is we can deliver pages of memory from the physical memory to the JVM in a way that enables us within the Zing System Tools to know what the status of the cache is. That way, rather than when the JVM requests a new page for the heap, because it needs to allocate more objects, it may well get a page which is not in cache. We will intercept that, and if we've got a page available that is in cache, we'll give that to the JVM, and it's able to use that hot, use the cache lines and so on, and gets better performance through things like that. The other thing that we do is we don't keep the memory, which is what standard JVMs do. Standard JVMs will allocate pages of memory. They will make those available and dedicate those to a JVM, because we work with at the operating system level. We're able to say, okay, when the JVM doesn't need that page anymore, we can return it to the operating system, and that can be reused by a different JVM if we want, or it can be used by the same JVM later on. But again, in terms of cache hits, we can improve the way that works. We have a couple of other clever things that we can do, which are able to improve performance and give better reliability, if you like, with the JVM. So one of those is what we call quick release, where we can effectively steal the physical page from underneath a virtual page in order to reuse that for a garbage collection cycle. I won't go into that in any great detail, but the essential thing about that is it means that we can actually let the heap run almost to the point where it's literally 100% full before we need to run the garbage collector. And that means that we only need literally one free page of memory per thread that the garbage collector uses, and we can collect the whole heap. And that's regardless of how big the heap is. So that's a nice thing that we can do there. The other thing is what's called contingency memory. Because we manage a lot of the memory for the system, we can say, okay, if you have allocated, let's say, 8 GB to the heap of your application, you run your application and it's running quite happily, but then you get an abnormal situation where you've got a very heavy load, and suddenly the heap allocation and heap usage goes up to 8 GB. In a normal JVM, if you went up to 8 GB and then you tried to allocate some more space, you'll get an out of memory error, and the JVM will stop abruptly. Now, if that's a mission critical application, that's not a very good thing to do. So what we do is we reserve some of the memory that we have for the Zing system tools, and we call it contingency memory. That way, if you get to your 8 GB and you need a bit more to keep your application going, we'll actually let you go beyond 8 GB. At that point, if we can give you more memory, we will, and you can carry on allocating memory. We'll then run the garbage collector more quickly and try and bring you back into the range that you've set in terms of the maximum heap size. So again, it's a nice idea in terms of improving the reliability of your application. The one thing about this is that because of the way it works, we only support Zing on Linux. So there isn't a Windows version, there isn't a Mac version. Now, there's no realistic reason why we couldn't do that, but because of the engineering that's involved, we have decided that for server-side applications, for cloud-based applications, Linux is pretty much the operating system of choice for many people, so that's the one that we support. So let's talk a little bit more detail about the C4, the Continuous Concurrent Compacting Collector. So the basics of this are similar in some ways to other garbage collectors. And one of the big things about garbage collection is how the heap is organized. So rather than it necessarily being one big space, most garbage collection algorithms organize it into what are called generations. And you have a young generation where objects are first allocated, and then you have an old generation where once objects have been garbage collected a few times, or they've survived a few garbage collection cycles, they get promoted into the old generation. Now, with other algorithms, the way that works is that you can use different algorithms on the young generation and on the old generation. But for C4, because of the way our algorithm works, we use the same algorithm on both the young and the old generation. So the reason for having two generations is more for efficiency rather than using different algorithms on the way that they work. And that's simply because of the way that C4 works. It's very good, and we don't need to have different algorithms. In terms of how it works, it is truly concurrent. Now that's very important because it means that your application threads can run at the same time as garbage collection is happening. So there are no stop the world pauses. There is no compacting fallback. There is no situation where you'll get a long pause because of garbage collection work being done by the C4. It is parallel, which means we can use multiple threads to do each phase of the garbage collection. And it is compacting, which means we relocate objects in order to make the space that's available contiguous. We don't have to use free lists to identify gaps between objects, and then when we get massive fragmentation, we need to do other things. So no, when we're doing garbage collection, we actually compact things to bring objects so that the live objects are contiguous and the free space is contiguous as well. The algorithm that we use is a three-phase algorithm. It's called mark, relocate, and remap. Now, a key point about how our algorithm works is what's called a loaded value barrier. And this is what enables us to run the garbage collection fully concurrently with your application threads. And the reason for that is we have this thing called the loaded value barrier, which is essentially a read barrier. So every time you want to access an object, we will intercept that read of the object header, and we will look at what's going on. By doing that, we can make sure that two rules are always enforced, and two things are always going to be true. And those two things are that if we're in a marking phase, whenever you get a reference to an object, that object will have been marked as an object that is still in use. So that's a fairly simple thing. But the second one is that when you get an object reference, it will always point to the correct position for that object. Even if the object is being relocated as part of a compaction, when you get the reference to that object, it will be the correct one. So you can write data to that object, and you don't need to worry about issues of corruption of data because you're writing in one place whilst the object is moving, even though the garbage collection happens at the same time as your application threads run. But I'll explain more about that in a moment. So this allows for truly concurrent marking, truly concurrent relocation. A lot of people say, well, if you're going to intercept every read of an object, that's going to degrade performance of your application. And well, technically that's true, yes, but the performance overhead is really, really minimal. By minimal, essentially what we have to do is every time we reference an object in the JVM, we have to do a test and jump. And that's two instructions in terms of an x86 processor. But if you look at what the x86 processor will actually do in terms of optimizing that down into micro instructions, then it's essentially one micro operation. It can be done in a single clock cycle of the processor, which means literally a nanosecond that it's going to take. So even if you're doing intercepts of every object reference, unless you're using an application which would be almost impossible to write, which only works in L1 cache, then you won't see any noticeable degradation in performance because we're intercepting reads to objects. How does this work then? So essentially, when we need to start running the garbage collector and we decide that we're going to run it, the garbage collector will do pretty much the same thing that other garbage collectors do, which is it creates what's called a root set of objects. And the root set is essentially a list of all the objects that you can directly access from your code based on scanning through the stack and looking at the registers and looking at your static variable references. So that's the objects that are directly accessible from your code. Now, obviously in that root set, you're going to have objects that then have references to other objects, because they contain other objects. So we need to track those references and from the root set, mark each of the set objects in the root set and then track the other object references and do that again and again until we built up a complete graph of object references that are still valid. So the way that works is exactly the same way you'd expect, which is that we have garbage collection threads which take the root set and they look at an object and they say, okay, that object is still being used, so we'll mark it with a bit in the object header. We'll then trace the object references from that object and we'll mark those objects as still being accessible by the application. And we'll continue doing that until we find all of the objects that we can access from that initial root object. Because we are running in parallel, we can have multiple garbage collection threads which are able to process different parts of the root set independently. There's no issue of contention, so we can do that fully in parallel. So that works very nicely. Obviously, at this point, your application threads are still doing work. So they are creating objects, they're referencing objects, doing things that they need to do. What happens if an application thread comes along and says, I need to access an object which is not part of the root set, or wouldn't be part of the root set that's traced? Well, in that case, because we do this test and jump, we will look at the object header and we'll say, this object is not marked. So at that point, we let the application thread context actually do the marking for us. So we'll set the bit and say, okay, this object is still in use. But we would then also need to trace all of the objects that object references in the same way we do for the other objects in the root set. Now, we don't want the application thread to do that because that could delay the application and could cause a pause. So in that case, what we do is we say, right, we've marked that particular object. Now we'll give it to the garbage collection part of the JVM, which can essentially add it to the root set so that it can then carry on tracing all of the other objects. But the important thing is that when your application accesses any object, it will always have, when you get the reference back, it will always have the object marked as being valid. So we don't miss any objects being used by applications because the application is running concurrently with the garbage collection. The next thing we do is we do a relocation phase. So this is where we do compaction. So we will have a situation where we've got a number of pages in our memory which represent the heap, and we have another number of objects which are distributed through the heap space. In order to eliminate the gaps between those and eliminate fragmentation, we need to calculate where to move those objects to. So we will figure out that in order to compact those, we will move A to A prime, B to B prime, C to C prime, and so on. What we're then able to do is to actually move those objects. So we will move an object from A to A prime. And when I say move, it's actually copy because we don't really move it. We don't eliminate the data. We simply copy the object from A to A prime, B to B prime, and so on. And as we're doing that, we'll also record in a side table all the changes in reference. So where A has been moved to A prime, where B has been moved to as B prime, so on. So that's the idea of compaction. Then we need to go through remapping. So the remapping phase. So what happens here is that the garbage collector will say, okay, we have this side table which says A goes to A prime and B goes to B prime. It will then read the information from there. And let's take the example of A to A prime. It will then look at the object header for A, and it will update it to point at the right position for where A has been moved to. So now the object header says it points at A prime, the new place where we moved the object to. And it will mark that that object has been moved and the reference has been updated. When the next thing comes through, we'll do the same thing. And then because our application threads are running at the same time, what will happen is an application thread will try to reference an object. At that point, again, we do the test and jump, and we look at that and we say, oh, that object hasn't been marked to say that it's been updated to its new position. So at that point, what we will do is we will retrieve the information from the side table for that object. We will change the reference to where that object is now positioned, and we will mark the bit in the object header to say that that has been updated. That way, when the application gets the object header reference back, it gets the right address for where the object has been moved to. And there's no issue with the application thread ever getting the wrong address for where the object is. In the case of where we're actually relocating the object, we will put a lock around that, but because each object is typically very small, the time that is required for that lock is very small as well. So everything works with guaranteed preciseness and guaranteed correctness. Now, because of this way this works, we can actually scale up to very, very, very big heaps. We can actually scale all the way up to 8 terabytes. And regardless of how big your heap is, the pause times associated with that garbage collection will not increase in time. Pretty much every other garbage collection algorithm out there, if you increase the size of the heap, you increase the length of a pause when you do a major garbage collection, because the length of the pause is proportional to the size of the heap, not the amount of data. With this algorithm, there is no degradation. So you make the heap as big as you like, up to 8 terabytes, and you won't see any degradation in garbage collection pause times. Nice thing about that is that often we see people who divide up a workload amongst several JVMs to keep the heap sizes reasonably small, so the pause times are reasonably small. Now you don't need to do that. You make the heap as big as you need for your application rather than trying to work the JVMs against the application. The other thing to say about Zing is, although it does run with very big heaps, it doesn't require big heaps. You can go down as low as 1 gigabyte of heap space. We don't go below that, but 1 gigabyte is the minimum, and you can use that quite happily with an application and it will do exactly the same thing. Typically what we find is that the bigger the heap, the better the algorithm works. So, you know, if you have more memory, make it available, you'll see better performance that way. Another thing that we've been doing more recently is looking at memory elasticity. And again, this comes back to the Zing system tools, where what we do is we actually are able to automatically expand the heap and contract the heap to use the available empty memory. So this is a way of avoiding having to trigger a garbage collection pause more frequently. We can actually change the size of the heap within the bounds of what's been set in order to improve the way that that works. Again, if we are running on a system where the heap is not being used particularly heavily, so if you've got a situation where you may have had to allocate, let's say, up to 7 gigabytes of memory, but now you're running in a working set which is only 1 gigabyte, then the JVM will actually return that memory to the JVM, to the operating system, so that it can be used for other things within the machine. This works very well in terms of multi-tenant environments. So if you're running things like containers, multiple containers on the same physical machine, that's a very good example of where that works nicely. Also, it reduces the need for having to figure out what size the heap needs to be, because you can say, okay, well, the memory gets given back to the operating system, so I can set the heap size to be quite big, but I'm not tying up all of my memory in order to do that. And this memory elasticity is actually working quite nicely in the current version of the Zing JVM. Another thing that we've been looking at more recently is Zing and Containers, because of course with the move to a microservices architecture, we're seeing a lot of people wanting to deploy into that, and so we've been working on how to improve Zing in that sort of environment. And the most recent thing that we've been working on is looking at how do you take containers to the next level in terms of orchestration using things like Kubernetes. So Kubernetes allows you to orchestrate different microservices to create the actual service that you're trying to develop. But one of the things that's a bit of a challenge is, because we used the Zing system tools, it was how to make the memory available within the container, within the Kubernetes environment. So now, if you look at the way that Kubernetes works, since 1.8, there's been this idea of device plugins, and you can set up daemon sets so that all the pods within all the nodes within a pod, can run the same thing and can have access to the underlying Zing system tools, and therefore you can run Zing within a Kubernetes and, let's say, Docker environment and have everything work really nicely. Also in terms of extended resources and things like using the device plugin resource. Right, so how do we prove that what we're doing works really well? So we need to measure the performance of the platform. And in this case, what we're doing is we need to measure what actually is happening with the platform underneath your application, not the performance of your application. So it's not like running benchmarks on your application. It's like, how do we actually measure the performance of the JVM? So we've created this thing called JHiccup. And JHiccup is essentially a little tool that you can run in a JVM that's running your application, as a separate thread. So it's a thread that runs alongside your application. Doesn't interact with your application at all, so there's no effect on your code or anything like that. The thread spends most of its time asleep. So what happens is you start the JHiccup thread and it will go to sleep for 1 millisecond. When it wakes up, it will look at the system clock and it will say, I expect it to be asleep for 1 millisecond. What is the time now? And measure the difference between when it woke up and when it expected to wake up. If you think about if you're running on a machine where you have garbage collection pauses, then you go to sleep for 1 millisecond, there's a 20 millisecond garbage collection pause happens, your thread can't do anything, even the thread that's measuring JHiccup, so it has to wait 21 milliseconds or 20 milliseconds until it can wake up, and therefore it monitors the difference in time. From that, we can generate some histogram log files, and then we can graph those to show how well things are working. So here's an example. So on the left-hand side, I've got an example of an application. This is Elasticsearch on a 128 gigabyte heap, and left-hand side is a graph of Zing, right-hand side is a graph of Hotspot. If we look at the graph of Hotspot, what we're seeing there is a very typical sort of garbage collection type of activity. So we're seeing small peaks, small spikes fairly regularly, which are the minor garbage collection pauses, and then a couple of infrequent pauses, which are longer, which are the major old generation garbage collection pauses. The bottom graph is just a percentile thing. So if you're looking at how you can match a service level agreement, then that's the kind of thing where you can say, well, okay, within 99.9% of the time, I can hit, however long the pauses are. On the left-hand side, we see a different type of graph, which is, still got a couple of spikes in there, and it's a more kind of wavy line. But of course, if you look at the one on the left, where of course high is bad because that's a pause time rather than performance, you might think, well, ooh, that doesn't look so good. Zing doesn't look as good as Hotspot. But what I draw your attention to here is the scale of the graph. So on the Hotspot graph, we're actually scaling from 0 to 8,000 milliseconds, so 8 seconds. On the Zing graph, we're scaling from 0 to 80 milliseconds. So that's a very different scale. If I show the same graph using both the same scale, what we actually see is a very different picture. So now you can see that essentially Zing eliminates all of those garbage collection pauses because it's literally flat across the graph. And the same with the percentile, there is really no change beyond a very small level right up to the 99.999th percentile. So that shows how Zing can eliminate those garbage collection pauses and keep your application with very low latency. So now let's talk about the Falcon JIT compiler, the other side of what we do. So there's a lot of discussion about ahead-of-time compilation and just-in-time compilation. So ahead-of-time compilation is what you typically do with C and C++ code. You can run it through a compiler, you generate instructions for a particular architecture, a particular operating system. But that has limitations on what you can do from a performance perspective, especially with Java. Java has dynamic class loading, and because of that, if you compile ahead of time, it limits the optimizations that you can make in terms of that compilation, because you may want to inline a method, but you don't know at runtime whether that method is coming from the class which you expect it to come from, or somebody is going to reload the class from a different or load a dynamic class at runtime and change the method that you are having to inline. So just-in-time compilation compiles as the application is running. We already discussed that. And the great thing about that is it has a complete picture of all the loaded classes. It's also able to have the profiling information, so it can make much more aggressive optimizations. It can use method inlining, it can use escape analysis to see what the scope of a particular variable is, and do things like that. So what we did was we looked at C2, the optimizing compiler, and we said, how can we improve that? And initially, we looked at it and we said, well, it's very old. It was written in 1998, and it's very difficult to make changes to it. It's a real kind of monolithic piece of code that's very hard to maintain. So we looked around and we found that there was a compiler project called LLVM. This is an open source project. It's supported by a lot of big names in terms of contributions, so Intel, ARM, Sony, Apple, Microsoft, and others. all contributing to that project. Now, initially, the design of Falcon, the design of LLVM was around ahead of time static compilers. But we said, okay, let's take that and use it for JIT compilation. So we integrated the LLVM technology into the JVM, made it work with the garbage collector, made it work with the idea of running applications, and then we contributed that code back to LLVM so that other people could use it as JIT compiler as well. The great thing about LLVM is it's a very modular design. So it's very easy to include new features. And as I say, because of this number of other contributors to the project, every time we refresh the source code that we use from LLVM, we suddenly get a whole bunch of extra features and improvements that are made available because it's a number of different people working on this, not just us. Lots of kind of optimization areas that we've been working on. I won't go into these in too much detail because they tend to be fairly sort of technical. First one is what's called lazy materialization. And this is looking at how to improve the speed at which the compiler works, because it's how the JIT compiler actually reads objects, whether they're like methods or functions, into memory from what's called a bit code, which is how LLVM uses an intermediate representation of code between the different phases of the compilation. Like I say, it is quite involved, but it means that by doing that, we can actually improve the speed at which the compiler works, not necessarily improving the compiled code, but improving the speed at which the compiler itself works. And because we're doing just-in-time compilation, faster means better. Other thing that we can do is more inlining of code. Again, this is like method inlining so that you can eliminate the stack calls, stack frames that you need to generate for that. Keeping objects on the stack rather than as objects on the heap. All of those things are much better. Better intrinsics, enhanced escape analysis. Escape analysis looks at the scope of where an object is actually being used, so that you can, again, if you can do better escape analysis and identify more places where objects are constrained in their use, then you can do things like lock elision, so removing the need for locks, which often can slow down code. There is a new LLVM pass manager that's been implemented. Again, this is about improving the speed of the compiler itself, because the pass manager deals with the different phases of the compilation and how information is trying to avoid the recomputing of results of the analysis of different phases of the compilation. So again, low-level stuff. And the last thing is the better use of vectorization. Vectorization is a very powerful thing. And if you look at modern processors, especially the very modern processors, in terms of Intel, they have AVX, AVX2, and AVX 512 instructions. The idea here is you have very wide registers, 128, 256, 512 bits. And you're then able to load up a number of, let's say, integer values into that very wide register and have a single operation applied to all of those values in a single machine instruction cycle. So this is what we refer to as single instruction, multiple data. And it's very good if you're doing anything that's sort of number crunching. Vectorization is very good. And what we've been able to do with Falcon is to find a lot of situations where the code that we can apply vectorization to is much better than the ones that you can do with other JIT compilers, because other JIT compilers will still use vectorization, but they tend to be restricted to certain places where it's obvious. With the vectorization we can do, we can even deal with a situation where we have if statements in a loop and still able to vectorize it. Benchmark velocity. This is a good way of showing how we're improving the way that Falcon is working. So what this shows is where we do a number of benchmarks. So we've got Spec JVM, we've got LMAX, we've got Cassandra, Decapo, Disruptor. So if you know about benchmarks, these will be names that are familiar to you. And what we've done is to run those benchmarks on different versions of our code, and essentially we're looking at where we get results which are not as good as Hotspot versus results which are better than Hotspot. And the general shift is that we're moving more and more things to the position where we get much better results than you would with hotspot in terms of the code. There's still some that we're getting slightly worse results, but we treat all of those things as essentially a bug. So we look at wherever a benchmark doesn't run as fast, we try to identify how to make it run better. And essentially what this is showing is that now we're getting, in case of some of these benchmarks, we're getting 190% or 200% faster results than we get with hotspot. Another example, Apache Arrow is an open source project, and we were working with a customer who was using this, and one of the things that they were doing was looking at how to try and improve the performance of this because it's very file IO intensive. And when they tried running it with Zing, they instantly got a 50% performance improvement, and so they wanted to figure out how that was working. And what they've been doing was actually looking at the underlying code in the library, the Apache Arrow library, and they'd rewritten part of the very low level part where it does a lot of the file I/O. They'd rewritten that in C++. The idea being that by rewriting it in C++, they could get a benchmark for how fast the code could actually work if they were able to tune Java to work that way. So it gave them a baseline for the maximum possible performance they would get from Java. And by doing that, obviously, by running the C++ compiler, they were able to generate native code. They could apply lots of optimizations to that for specific operating systems and so on. What they found when they looked at the code that was generated by the JIT compiler in Hotspot and compared it to the one that was generated by Falcon is that the Hotspot JIT compile code was far less optimized. And there were lots of places where, obviously, by being unoptimized, it was getting lower performance. What they found when they looked at the Falcon code was it was almost identical to the code that they generated from the C++ code. So rather than having to rewrite it in C++, they could just use the existing Java code and get the same level of performance. So it's a nice kind of example. Last thing I want to talk about is ReadyNow. And as I say, the idea here is to go back to our graph of performance and say, okay, so we've got this warm-up phase, warm-up time. That's how long it takes to get to the optimum level of performance for an application. Problem is that with an application, what happens is you run your application and you let it warm up and it runs and it's all good. Then you have to stop it for whatever reason and you restart it. And when you restart it, it has to go through the same application warm-up time, has to do the same analysis, has to do the same profiling, has to do the same compilation. Why do we have to do that? Well, there's many good reasons, most of which are to do with the way that the JVM has been designed. So what we do is we allow you to run your application until it's nicely warmed up, and then you can record a profile. Now, the profile is not simply a snapshot of all the compiled code. What you can't do is simply record all the compiled code, and then when you restart the application, just reload all that compiled code and take off as if you were running when you stopped. Can't do that because of the way the JVM's been designed, because of the way the JVM has been specified. So what we record in the ReadyNow profile are four things. Firstly, we record all the classes that are loaded. Then we record all the classes that are initialized, which could be a subset of the first loaded classes. We record all the profiling data that was gathered by the JVM up to the point where you gathered the profile. So you're effectively recording all that information about what went through the system and which methods were hot, which methods were cold, things like that. And most importantly, any speculative optimizations which failed. So in order to get to that point, which things did you have to throw away the compiled code and then recompile it, which is very inefficient. We can gather that data over a much longer period. You don't have to wait just a couple of minutes and then record a profile. You could run your application for a day, you could run it for a week. You could collect profiles at different points. So when your application is running one particular workload, you record a profile, running a different workload, different profile. That way, when you restart your application, you can say, oh, okay, I'll use that profile because it's a Monday morning, or that profile because it's Friday afternoon. This gives much quicker startup, significant reduction in de-optimizations. And essentially what we're able to do is by doing all of this work as the JVM starts up, we're able to load, initialize, and compile most of the code before you get to the public static void main entry point of your application. And that's really good because if you've got like a trading application and you want to have it ready for 9 o'clock when the bell goes, then you can start up your application at 5 to 9, use the profile, compiles all the code, and you're ready to go. So if we look at a customer application that we did some profiling of, what you see here is the latency. So lower is better. And if you look at the orange line, we see sort of up and down until it drops down into the low latency part. And that's without using ReadyNow. So this is where we can see that the code is being compiled. There's de-optimizations happening, all those sorts of things that are happening in the usual way. The blue line is where we use ReadyNow. So we're simply saying, okay, as the application starts, we compile all the code, load all the classes, and so on. So that gives us much better performance at startup time than we would get using or without using ReadyNow. The other thing that we've done, and this is the most recent thing that we've been working on, is what we call compile stashing. And compile stashing is, if you remember, I just said that you can't just record take a snapshot of the compiled code and then reload it. So what we thought we'd do is we'd take a snapshot of the compiled code and then we would reload it. Now, not quite as simple as that, because the way that works is a little bit more complicated. So what we found is that speculative optimizations are essentially responsible for over half of the speed improvements that we get in terms of the JVM. So if we can get more speculative optimizations and we can take the code for that, then we get much better performance. So what the Zing JVM does is it stashes the compiled code for methods. So you compile a code, you make it run, everything's good, including speculative optimizations, and then you put it in a file and you're able to reuse it at a later point in time. But the way we do that is we don't break the contract that we have with the JVM specification. So we can't simply just reload all that code when we start up the JVM. So essentially what happens is that we start the JVM and the JVM needs to compile certain methods. So what it does is it says, okay, here's a profile, which is almost like a fingerprint of a particular method. So it's the name of the method, the signature of the method, but also the profiling data that's associated with that method. And then we try to match that against the code that we have compiled. If the profiling information matches, then we say, oh, okay, we can reuse that compiled code. We don't have to recompile it. We simply reload that as if the compiler had compiled it for us based on that profiling information. If it doesn't match, then we go back to the JIT and we say, okay, now compile the code based on this profiling information. So it's essentially like putting a code cache in between the JVM and the JIT. So if the code is already there, we use it based on the profile. If it isn't, we go to the JIT and we recompile. So it's a very nice way of doing things, and it works very well. So just to summarize, this is the graph, going back to what we saw before. And I've kind of overlaid the two graphs onto each other. And in terms of what we do with Zing, essentially we use C4, our garbage collector, to eliminate the pauses that we see once the application is warmed up. The dips in performance because of the pauses associated with garbage collection. Falcon is our JIT compiler, which raises the level of performance of the application overall. So even when you get to the steady state of performance, because we're using Falcon, because we're using more optimizations, we get better performance than you would get with your traditional JVM. And then with ReadyNow and compile stashing, what we're doing is we're pushing that warm-up phase, the sort of slope of the warm-up out, so that we get a very, very steep warm-up phase at the beginning. So literally, a couple of transactions and we're up and running at full speed. So the idea behind Zing is to start fast, to go faster, and to stay fast. So those are the three things: start fast, go faster, stay fast. And the idea is that it is a simple replacement for other JVMs. You don't have to recode anything. There's no rewriting your code to work with the JVM. It's exactly the same. So the only thing you have to do is essentially get rid of a whole bunch of command line flags, which you don't need anymore with Zing. You can try it free for 30 days. So if you go to azul.com/Zing trial, you can download it, you can install it and test your application on it, use JHiccup, create some nice graphs, show your boss how running it on Hotspot gives you these big spikes. Running on Zing gives you a nice flat line, and everybody's happy and everybody wants to use Zing, well, at least hopefully. So with that, that's the end of the presentation.